Did the rocket gain the same amount of momentum as the object lost? Well, obviously you have to always conserve momentum. So the rule would be, of course, every physicist, I think, of any character says you have to serve, Professor Lewin says, nature can deal with kinetic energy one way or the other, but nature can't finagle momentum. So the argument would be, yes, you have to conserve the momentum. And I'm going to shoot an object. Let's just say the object weighs the same amount as the truck, just to make this more fun. So then the masses will be the same. So it will be a lot less complicated. So the heavy mass, I got a real titanium ball that weighs as much as the truck. So both of those things are moving 10 miles an hour. Now I'm going to apply a force with the spring, okay, that's equal to the momentum, okay, of this half of the total momentum of the truck and the object. Right? So that's what it's equal to, half of that. Because it's going to stop this from moving. So this is just going to drop down. Okay, it pushed the weight against its force. So its momentum, its mv, it also had to absorb. So it's not only going to get a boost from absorbing the mv to push the object backwards. So it gets plus, so it has mv, and now it's going to get another unit of mv. All right, from the push, and then another unit of mv from the fact that it doesn't have that extra weight anymore. So now it's going to get an extra v. All right, so the point is it'll go 3 times as fast. So now you got 3 units of velocity here. Okay, and you have 1/2 the mass. And you're going 30 miles an hour. That would be my argument. Made off the top of my head, of course, to your thought. So it didn't really matter. But yes, I did make a mistake. All right. In terms of my off the top of my head explanation, was in fact incorrect. Okay, so I have a spring and I put it between an object, right? So the simple argument is going to be that if I compress the spring to this distance, okay, it's going to have, let's just say 20 units of, foot-pounds, whatever, 20 pounds of pressure. Okay, right. So I said this would end up going 30. That was incorrect. The same thing is going to happen. Okay, it's going to apply 10 this way because it's going to stop this one from moving, and this one's going to go 20. So I'm going to end up with 1 block going 20 and 1 block going 0. Right? And so his argument is well, that's only 20. So I released the spring, but I only have what I started with, which is 2 10s moving in one direction. So I only had 20. So I have the same amount of energy. But you have to think about it in terms of what energy really is. And what energy really is you actually had absorbed energy moving this way. So it was inside the mass. And the energy is inside of this mass. All right. And what did you actually do? Well, you released this energy into the field. Okay. So now that energy is free. So the energy goes when, if both objects are moving, when you stopped this one from moving, what did you do? You applied a force that forced this force to be rejected, to be ejected. So the force that was moving it is no longer in it. So it's been released. Okay, so that's what the motion of the spring this way did. It released force into the field. It put it back as free energy in the field. And this one just absorbed 10 more. So it owns 20. This one released 10. Yeah. And so that's your 30. This one has 20. You release 10 here. That's the 30. You start with 20. You let the spring expand, adding 10. Now you've completed your math. All right. So that's the more accurate way to describe the thing he did. I mean, really, it's just a simple experiment. You're just saying, can springs release energy without changing the world? And I guess the simple argument is, of course not. That's conservation of change. When you compress the spring, you change the world to do it. You took energy from something and put it into the spring. And now when you release it, you have to account for it. Because obviously it didn't create positive momentum. That is, the spring's compression turned into the unmotion of something, not the motion of something. The work was done releasing energy into the environment, not consuming energy out of the environment. But we do. So in our frame, there's clearly a missing component. I started with 20 MV and I ended with 20 MV. And that's the part that's broken. But it's only broken because you have to understand that there's 10 MV that's not moving now that was moving. So obviously that's another 10 units of energy required to make that happen. Okay. Freeing energy require you have to use energy to liberate it. It doesn't matter. The third law is not about energy. Yes, it's about momentum. So we already know what the momentum has to be. There's no choice, okay? You can't play this game that the spring can expand and it can give, 1 unit of momentum this way and 10 units of momentum that way. We already know that can't happen. The explosion can't do that. It doesn't happen in the